Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to start doing Bayesian inference for data coming from a Poisson likelihood, okay, from a Poisson distribution. Let's begin. So, Bayesian inference for Poisson. Okay, so as you can imagine, our starting point will be talking about those two very important ingredients to carry out Bayesian inference from a Bayesian perspective, the prior and the likelihood. Okay? Okay. So, our parameter. So let me use the letter, we could use the letter lambda or mu. In our textbook, the authors use mu to refer to the mean of a Poisson. So let's use mu. Let me remind you what the likelihood looks like. First, we are going to talk about the likelihood for a single observation. Okay, that will be our starting point. So using our notation, it would be the conditional probability of observing a particular value y given a particular value of the parameter mu. Okay? Now, this guy, and we know this from sta360, that the probability mass function for a Poisson with parameter mu looks something like this. It's going to be mu to the y power divided by y factorial times e to the power minus mu. Okay, e to the minus mu. And we know that the support, right, is y equals 0. Y equals 0, 1, 2, 3, so on. Okay? Now, let's talk about the other important ingredient in Bayesian statistics, right? In Bayesian inference, the prior distribution. So, prior distribution. In general, you know, we refer to that guy as P, in this case P of mu. It's a distribution, right, a probability distribution, and to be more specific, the kind of prior that we're going to be considering here is the conjugate prior. Okay? So based on our experience with data with binomial likelihood, what we did when we talked about the conjugate priors back then is ignore the constants, right? Ignore the terms that do not involve your parameter. Just pay attention to the kernel, right, of your likelihood, and try and find a family of distributions that resembles that kernel of your likelihood. So by looking at this guy, right, if you ignore y factorial, which doesn't involve our parameter of interest, mu, you have seen something like this before, right? Remember gamma distributions from sta360? Well, it turns out that that would be the conjugate prior when we are considering data with a Poisson likelihood. Okay? So, now, let me say something more about this probability density function that we're going to be using here in this video. There are different ways of, mainly two ways of writing the probability density function for a gamma, okay? For a gamma random variable. This is one of them, okay? In your textbook, they have two parameters, v and r, and that constant that I am writing would be the normalizing constant, would be the constant that makes this expression in terms of mu a legit probability distribution. So in terms of, in this case, the variable mu, the way that you would write the probability density function of a gamma with parameters r and v is this. V to the r divided by gamma, the gamma function evaluated at r, mu to the r minus 1 power e to the minus v times mu. Okay? And the support for that gamma is we need those mu's to be positive. You could include 0 as well, but okay. Anyway, so the one that we are considering here, right? Let me just point that out. This is a gamma with parameters r and v. And this is the PDF used in your textbook. Again, there's a different way of writing gamma distributions, and the difference lies here in the exponent for that exponential term and the constant that you would have here. Okay, and I might include both just for completeness in our lecture notes, but in this video we're going to concentrate on using this expression for the gamma probability density function. Okay, so now what we're going to be doing is obtaining the posterior, okay? And we're going to do this step by step, very carefully, okay? So posterior distribution. We know that the posterior distribution would be this conditional density, probability density function, the probability that mu, the probability of mu given y, okay? And we know that, well, this is going to be the same as the joint divided by the joint of mu and y divided by the marginal of y, right? So let me write that down. Joint of mu and y divided by marginal of y. Okay, so we know that we could find the joint using our prior and our likelihood, right? The product of prior times likelihood is going to give you that joint. And then here, this guy, the marginal would be the integral, right, of the joint with respect to the other variable. The other variable would be mu, and since mu is positive, it would be the integral from 0 to infinity of that product, and we are integrating that product with respect to mu. Make sense? Got it? Okay. So the numerator is not a problem, right? It will be just the product between this guy and this guy, right? So let me refer to that guy like that, to that product as the numerator. Numerator is going to be this times our prior. Okay? So we could, you know, make it look nicer. We could just, oh, sorry. We could just rearrange these guys here. Let's place that constant here first, right? And we could rearrange the other terms here, right? It would be the same as mu to the power r minus 1 here. Then we don't need this anymore. And then we could factor out that negative mu, right? And then we could have something like this, right? We could have, oh, sorry, we want to have it here in the exponent. We could have negative mu 1 plus v, right? Agreed? It's the same, right? So now we no longer need that. Make sense? We just did a little bit of algebra with the exponents. Okay? Okay, so that's the numerator. Let's talk about the denominator. Let's find that integral. So it's the integral with respect to mu of this, right? So let me write down that integral from 0 to infinity of this. With respect to mu. Now, when you look at it, at this point, you have been doing a little bit of Bayesian statistics, right? So at this point, you should immediately know what we're going to be doing next, right? We will try and turn this into the PDF of a legit probability into the PDF of a legit random variable, right? So anyway, in this case it should be clear that this guy, right, looks like the PDF of a gamma, right? So when we are integrating with respect to mu, so let's pull out the constants, right, the terms that do not involve mu. So V and R are constants with respect to mu, right? They come from the prior distribution, okay? That y factorial is also constant with respect to mu. So let me write this down here, and let me pull out that y factorial here. Let me place it here in the denominator like that. Makes sense? So we just, you know, pulled out those constants, and we left only inside the integral the terms that involve mu. Okay? Now when you take a look at this guy here, you go, that looks similar to my prior, and that's the plan, right? That's why this guy is going to be the conjugate prior. So we compare to this and we go, the argument of the function mu to the power something minus 1 e to minus another constant times the argument mu, right? So we make a little change of variables, if you will, here. So let r star be y plus r, and v star, right, v star be 1 plus v. Then what we're going to have inside that integral, right, will be something like this. We have r star and we have v star Now we would like to have a gamma PDF here, right? So in order to have that, we need an appropriate constant, right? That constant is given in terms of those parameters r and v, or in this case r star and v star, and it looks like this. So let me borrow this guy here. That's the one we need, but with v and r star. So we need this guy here, star. Let me, star. We need r star as well. R star. Okay. So, and these are constants, so no problem. We can multiply by a constant here, but if we do that, right, in order to do things legally from a mathematical standpoint, we have to, multiply by the reciprocal. So let's do that outside the integral. So we are dividing by gamma evaluated at r star. Well, let's multiply by that. We are multiplying by v star to the power r star. Let's divide by that. Okay, so now this guy, the integrand, the function that we have inside our integral is the integral over the entire support of a gamma with parameters v star, well, r star and v star, right? So that integral is going to be 1. Right? Agreed? Again, this guy is a gamma with parameters r star and v star, and that's a legit probability density function. We're integrating over the entire support. That must be 1. Okay? So, and then we could just do the math here, right? Let's find the posterior. This happens to be our denominator, right? So finally, our posterior, we know, is given by that. Let me copy paste that, and then that happens to be the same as, let's write our denominator and our numerator. So first the numerator is this guy here. Let me copy and paste that guy. Numerator. And the denominator, right, is this guy here. So note that that constant v to the r divided by gamma evaluated at r, right, and that y factorial, those will go away, right? So what we're going to have left is just that expression that we have here, mu to the power y plus r minus 1 e to the minus 1 plus v times mu divided by this. Okay? So let me write that down. So here what we have is that term times that term, because you know that y factorial will cancel out with this one, and that with that. Okay, then in the denominator we only have this, but then that is equivalent to having just v star to the r power divided by gamma to the r power, right, times this. Make sense? So we have this, and this is the same as this, but we will have v stars and r stars instead. Make sense? Right? Now, remember that v star is 1 plus v, and r star is y plus r, right? So this guy here is r star, and this guy here, oh, let me do it like that, r star, and this guy is v star, right? Star. Makes sense? We just did a little bit of algebra. This divided by gamma evaluated at r star divided by v star to the r star power is the same as v star to the r star power divided by gamma evaluated at r star, and y plus r is the same as r star, and 1 plus v is the same as v star. And that's what we did here. We substituted that. So what we realize is that our posterior distribution is a gamma with parameters r star and v star. So gamma with parameters r star and v star. So we were right. The gamma distribution is going to give you the conjugate prior for data with a Poisson likelihood. Make sense? And just let me remind you that r star is y plus r, and v plus 1. Make sense? Okay, so let's recap. Very quickly recap. So in this video we started studying data coming from a Poisson distribution, meaning data that could be modeled using a Poisson likelihood. Okay, so the kind of prior that we are considering is a conjugate prior. Taking a look at the expression of the likelihood, we decided that it would be a good candidate for the conjugate prior to use gamma random variable. We used the way that they express a PDF of a gamma with parameters r and v, as the authors of our textbook do, right? We found the posterior distribution very carefully, step by step, right? We know that this is basically Bayes' theorem. So we found the numerator and then the denominator. And after doing the calc and algebra, we were able to show that the posterior distribution, the probability of mu given y, has a gamma distribution with parameters r star and v star, right? Make sense? Oh, this should be r, right? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you later. Bye.